I am Professor Miller, and this is an example of correlation and regression. My two variables are the annual tuition charged by colleges and the median starting salary of the graduates of these 86 colleges in my sample. To see if there's a relationship between them, the first thing you should do is draw a graph. The graph is called a scatter plot. And here are the three possibilities. Probably as tuition goes up, salary goes up as well. That's called a positive correlation. It's possible but unlikely that higher tuitions lead to lower starting salaries. Can't imagine that happening. But it's also possible that there's no correlation. A higher tuition may or may not lead to a higher salary. So let's look at this example and see how to create a scatter plot and look to see if the two are related. First thing you want to do is select the data that you want to plot. Go to Insert, Chart, Scatter Plot, and there it is. Can't really tell. Looks like maybe there's a slight upward bias, but how do we know if it's a no correlation situation or a positive correlation? Well, we need to quantify this. Excel has a nice feature here. If you add the trend line, that's going to be the regression line. You can also display, under more options here, you can display the equation and what's called R squared on the chart. So here we have R squared equals 0.1941. R is the correlation coefficient, and it won't be hard to get that, which is the square root of R. So the correlation coefficient is R. That's the correlation coefficient for a sample. There's a formula for it. Here's the formula. The interesting thing about the formula is it contains in it these quantities that look like standard deviations. There's the standard deviation for X. There's the standard deviation for Y. So they gave me 0.1941 as R squared. That's taking the square root of that, you'll get the same value, 0.441. Now R will always give you a value between -1, that's a perfect negative correlation, and 1. If the correlation were 1, then all the points would lie right on a straight line, and you could perfectly predict the value of Y for a given value of X. So this value, it's not that close to 1. The question is it significantly positive? Is it significantly greater than 0? There's a hypothesis test that can be done to determine that. You want to see if the null hypothesis would be that the correlation is 0, and the alternative hypothesis, what we think at this point, having computed it, is that it's positive. As you might expect, there's a bell-shaped curve associated with correlation coefficients from samples. Here's R, 0's in the middle. It's a t distribution. You can see the standard deviation that was computed here. That's from my sample, so it's t. I'll use alpha equals 0.025 for this test. 0.025 in the right-hand tail. Using the t dot inverse and the area of 97.5%, that's below that. Interestingly, the degrees of freedom, 86 minus 2. You're used to doing n minus 1, but because this is bivariate data, you lose 1 degree of freedom for each of the standard deviations that you used as estimators for the population standard deviation. That gives me my t crit, which is 1.989. As I said, that's t crit. T star now is r over square root of 1 minus r squared over, there's that n minus 2 again. Again, here's that r squared in this formula. R squared was 0.1941. Interestingly, that can be interpreted as a percentage. R kind of looks like a percent. It's always a decimal value, but remember, R can be negative. R squared can be interpreted as a percent. It's the percent of the variation in the starting salaries that can be explained by changes in the tuition at the various colleges. So I compute this, and it gives me 4.498. Somewhat surprising how high it is. This 0.44 turned out to be highly significant. It's very much more than 0. So reject HO, probably because the sample size is pretty large. Accept HA. And what does that mean? That means as tuition expenditure goes up, that the salary generally increases as well. Notice I say generally because it doesn't happen every single case. It's just a general trend. So that's a positive correlation. That's correlation. Now let's look at regression. So we've established that there's a positive correlation. Now we want to exploit that by writing down the equation of what's called the line of best fit, and then we can use that to guess what the starting salary would be at a certain tuition level. I put 10,000 as an example. So we want to find the equation of this line. Equation of a line, you should recall, is y equals mx plus b. Here for the regression equation, when you use y hat, that means the estimated value. There could be an x value for which there is a y value. The y hat value would be the line, the value of y for the point of the line for that particular x. Could differ from an actual data value. So there's a formula for m. Kind of interesting. It's not surprising that it looks like the correlation formula sort of has to be, because this is the formula for the slope, and think about it, if the slope is positive, there must be a positive correlation too. So this is just the formula. It's derived from the calculus. If you think of it, what you're doing to find this line is finding the best line, that is, the line for which the errors, that is the distance from these points to the line, is the smallest of all possible lines. And actually think about this line. At a level of $10,000 tuition, there are probably a lot of colleges that charge that tuition, and this would be the mean, the expected value. So this regression line is a line of means, expected values for each of the x values. And so these distances from that are deviations from the mean. And in fact, in deriving this formula, it's just like the standard deviation computation. We actually minimize the square of that distance as opposed to the distance itself. I'm not going to emphasize the computations here. Excel gave me these values. If you recall, when I put that on the graph, this was the equation of the line of best fit. What I do want you to do, though, is to interpret the meaning of these values. Let's start with this one. This is called the y-intercept. The y-intercept is computed, again, there's some theory here, and the theory says that one point that must be on the line is the point x bar, y bar, the middle. If you recall algebra class, when you were finding the equation of a line, once you found the slope, you would plug in an x and a y from one of your data values and then solve for b. Here you can't use any of the data points because you don't know that any of those points are on the line, but you can use this one. So b can be computed by doing y bar minus m x bar. That's how I compute b. But what does it mean? So y-intercept, the y-intercept is the y-coordinate of the point where the line crosses the y-axis. What's the x-coordinate there? 0. So that's the way I interpret it, is the value of y when x equals 0. So this would be the starting salary predicted if the tuition was 0. You'd like to go to that college, it's free. Now, what's the interpretation of the slope? The slope is how steep the line is. I told you here, slope tells you whether it's going up or down, and then how steep is it. And we sort of unitize that. For every 1 unit I go over, I go up 0.21. It's the change in y for each 1 unit increase in x. So in this case, starting salary increases by 21 cents for every extra dollar spent on tuition. Now, what's the point of all this is to be able to make predictions. So if I know the slope and the y-intercept, I can plug in a value for x into the equation of a line. For instance, I gave 10,000, plug that in for x, and there you see the predicted value of y for that x. So that's what regression is used for.